This presentation is about battery charging systems. Batteries are charged by applying a high enough voltage to them, but the rate of charge is not constant. In the first split second, the very lightweight electrons move down the outside of the connecting wire at the speed of light. When they reach the battery which is being charged, there's a problem, and that is that the charging current inside the battery is carried by much heavier ions, and they don't move at the speed of light. A tiny fraction of a second after switching on, the electrons reach the bottleneck of the heavy battery ions, and so they pile up in a great cluster. This is the same effect as if a much higher voltage was applied to the battery to charge it. This causes a much greater rate of charging, but this effect only lasts for a fraction of a second. And if you're using a DC charging source, this arrangement only occurs once during the entire charging session. However, if we choose it, we can arrange our charging circuit to do this switch-on style of charging thousands of times every second. For example, Lawrence Chung produced a charging system which is a modified Joule-Thief circuit, and he states that it is 10 times more effective than ordinary charging. This is the circuit, and this is a possible physical layout. This is a circuit that I've used myself, and it's very effective. The circuit switches the charging voltage on and off very sharply, and it does it about 290,000 times a second. Now that's 104 million times an hour. A much more powerful version of this style of circuit has been produced by Alex Kor of Russia, and his version uses a high-performance transistor and generates voltage spikes large enough to charge 4 batteries from one driving battery. So you have 4 batteries being charged by pulses coming from the circuit. The circuit is self-oscillating. It has an air core 200 turn coil of bifilar wound ½ millimeter diameter enamel copper wire. This is just wire wound on a plastic cardboard cylinder. The circuit is extremely simple. You've got a resistor which feeds some base current to the transistor. Transistor is a very powerful one, an MJE 13009, and there is a small capacitor across the resistor to specify and control the frequency at which the circuit oscillates. That combined with the coil, and the neon bulb here is not actually part of the circuit itself. It's a protection device to protect the transistor if it should get disconnected during the charging operation. Now, that's about as simple a circuit as you can get. The circuit could be physically laid out like this. You have your coil wound with 2 pieces of wire. One is marked in red, one is marked in blue, and they go through to the drive battery and the 4 charging batteries, and the circuit is built up using screw connectors which are available in the local hardware store. It is possible to run a load off batteries which themselves are being charged. One system that does that is known as the Tesla switch, although it's unlikely that Tesla was ever involved with the circuit, as it's shown in the Carlos Benitez patent GB 14311 of 1916. The staff of the Electrodyne Corporation of America experimented with this circuit, which, shown in Volume 1 of the Manual of Free Energy Devices and Systems, published in 1986. They tested the circuit for a period of 3 years using ordinary 12-volt car batteries. However, their testing altered the batteries which they were using, and those batteries ended up being 36-volt batteries. lead acid, and conditioned. Conditioned batteries operate in a very different way to ordinary batteries. They charge much faster, they have much greater capacity, and they have higher voltage, but they lose their conditioning if left unused for some time. A battery becomes conditioned if pulse charged and then discharged repeatedly. After many of such charge-discharge cycles, the conditioning change starts to happen. So please bear in mind that the Electrodyne Corporation staff used their batteries repeatedly for 3 years, and at that stage their batteries were 36 volts and conditioned, and that's probably why nobody else has managed to get their circuit operating in the way that they described it. This is the circuit which they used, and it needs to have an inductive load such as a motor, but it can output 30 horsepower, which is 22 kilowatts, and it does that continuously. Now the circuit has 3 on-off switches, 3 which are on at one time and 3 which are off at one time, and they cycle changing over. The blue ones go off, the red ones go on, and there are 4 batteries involved in the circuit, and they're connected very simply by 4 diodes, and the type of the diode is important. It's a 1N1183 style of diode. That's supposedly 35 amp 50 volt, but in actual fact that diode breaks down when it gets a large voltage applied the wrong way around to it. But when they do break down pardon me, when they do break down in the circuit as shown, they pass a sharp voltage pulse back to the battery, and being conditioned, the batteries recharge very rapidly. Sharp switching is always important with free energy circuits, and the Electrodyne Corporation staff use mechanical switching. They have a disc which has got 3 conducting sections to it, and they have got switches which press against those particular conducting sections, but they're arranged so that one set is off and one set is on as the disc rotates, and there are 3 of those discs on the shaft of a motor, and the motor has its own speed control, so you can set the rate of switching, and it effectively is a very quick and sharp way of switching. If you're going to build mechanical switching, then you might consider doing it this way. You use a motor which drives a drum which rotates along with the shaft of the motor, and pressing down on the drum you have got 3 arms with dual contacts on each of them, and those contacts are short-circuited when a metallic section on the drum passes underneath them. You have matching 3 pairs underneath the drum, and if you look at it from a side view, the arms at the top press down onto the drum, pulled by an ordinary coil spring, and the same happens on the bottom, but you notice that this one is touching a contact and this one has just finished contacting, so they don't operate at the same time, but the gap between the pieces of conducting material on your rotor drum are longer than the size of the heads of the bolts that actually touch these metal contacts. So you get an on, off, switching, but it's not even. You get on, off, and a pause while the drum rotates further, then you get an on, off, and a pause. So the operation is on, off, pause continuously, and the Electrodyne staff said that it was important at the rate that you switch this, and they said it should be between 100 times a second and 800 times a second. That is on, off, pause 100 times, or on-off pause 800 times a second. And they found that a load could be powered indefinitely with that arrangement. Here's a solid-state version of that particular circuitry. You have the 4 batteries and the connecting 1N1183 diodes, and the switching is done not by mechanical switches but by 6 TIP 3055 transistors, and those transistors are driven on and off with 6 audio transformers. Those audio transformers are driven by an oscillator, and they have 3 diodes facing one way on one switching set and 3 diodes facing the other way on the other switching set, and those 6 transformers are fed via a large capacitor from the oscillator. Now, those are effective in what they do, and that particular circuit has run very successfully, although it's not mechanical. Another design which keeps a battery fully charged while powering a much lower load is shown by a South African developer. His design has a continuous power output of 40 watts, and it looks like this. You have a series of coils around a rotor, and the rotor is driven round by the pulses operating in the coils, and the circuit is like this. The rotor has got 5 magnets in it. The north pole is facing out on all of these magnets, and there are 5 metal cord coils around the rotor. They match up in exactly with the positions of the magnets, and the system is started by spinning the rotor to begin. Then when a magnet passes by the core of this particular coil set, which has got 3 windings, one of the windings feeds a voltage through a resistor through to the base of a powerful transistor. This one is an MJE 13009. When the transistor switches on, it powers up these 2 coils marked as B, and those 2 coils create an electromagnet with the core of the coil, and that actually pushes the rotor on in its rotation, and that keeps the rotor going round and round forever and ever. Now those coils also feed, along with the 4 passive coils that just collect energy, they feed back to the system that is powering the transistor, and that system is this 100 microfarad capacitor, which charges up to 42 volts, because the charge from the collector of the transistor is also fed through a diode to the one battery in the system. The one battery is a 12 volt lead acid battery, and it powers an ordinary inverter with an output load. In this case it happens to be a bulb, but it also powers a step down transformer of 30 volts, and that feeds with a diode through to this capacitor, creating a 42 volt system that runs this particular transistor. The system is very effective and very powerful. Another system that does battery charging and is self-powered, because it charges its own battery while it charges a second battery, is this system here. It again has a TIP or 2N3055. The TIP is easier to work with because you can connect to it much better. The output from the transistor is fed via a diode to a battery which is being charged, and the battery supplying the power to this particular circuit is this one here, and it powers around through the main circuit back through the transistor. Now the cunning bit about this particular design is that there is a second cord coil which is up against the rotating rotor disc. The rotor disc has got 5 magnets embedded in it. The circuit on the left feeds pulses into the battery under charge, and it does that 5 times for every revolution of the rotating disc. This is the same way that a Bedini circuit always works. However, once per revolution, the micro switch here is operated by a bump on the disc, and that switches out the battery under charge and connects the driving battery through to a diode bridge attached to the pickup coil, and that happens just as this magnet is passing by the pickup coil. Now that feeds a small charge back into the driving battery and keeps it powered up all the time. This is what one of those micro switches looks like. It's got the 3 contacts that you see in the actual circuit diagram, and the lever there is operated when it's bumped into by the bump on the rotating disc. It's probably easier to understand this if you see the 2 parts of the circuit separately. The circuit on the left is the typical Bedini circuit, with the neon just protecting the transistor. It's not actually part of the charging circuit. The driving battery is connected through to the other side of the battery being charged, because if you don't do that, the power from the driving battery will just flow directly into the battery being charged. But this is the typical John Bedini style of battery charging. The recharging section here is very straightforward and simple. The batteries are switched over, and the driving battery is fed from the pickup coil through the 4 diodes to give it additional charge to keep it always lined up. Now, the pickup coils are in one straight alignment, and there are 5 magnets on the rotating disc. Now that means that when this magnet is aligned with this coil here on the right, the one on the left will be halfway between these 2 magnets. They never actually match. The same happens when this magnet moves round and lines up with this coil on the left. The coil on the right will be halfway between these 2 magnets. So the 2 parts of the circuit operate completely independently, and so an ordinary mechanical switch can be used to select between the 2 circuits. You can put extra coils on the system if you want. The thickness of the rotor is quite exceptional. It's nearly 2 inches thick, and it's made from laminate flooring material. It's 6 inches in diameter, and it weighs 2 kilograms. Now, just in passing, I'd like to make a suggestion, and it's only a suggestion. I've self-charged a 12 volt, 12 amp hour lead acid battery intended to be used in a mobility scooter. I've done it with just an oscillator and a choke. The charging rate was very high, and the battery continued charging after the circuit was switched off. Now, it seems likely to me that this could be replicated using a good pulse charger, so perhaps the Alex Core charging circuit shown earlier would work well with that arrangement. So the way that you would connect it then is you wind a choke of maybe 20 turns of reasonably thick insulated wire, and you put that between the pulses that have been fed to the battery and the circuit which generates the pulses. But as you have strong pulses going out to the battery, the choke will block off those pulses, and if you have a large capacitor, it will charge up with DC, which flows easily through a choke, and provide a solid power supply for the effectively Joule thief style circuit. It is a likely fact that this particular circuit would do very well at self-charging, but it's not something that I've actually tried as yet, And this is not a recommendation that you personally should try it either, as this presentation is for information purposes only. If you want, you can download this particular set of notes from this link here, and there's more detail on all of these things in the ebook, which is downloaded from the bottom link.